Hey everybody, and welcome to our first video on our next unit, which is going to be on liquids and solids, as you can see up here. Now, we're actually going to start this unit by talking about the stuff that we're actually not going to talk about in this unit on liquids and solids. We're going to start by talking a little bit about gases, which you learned all about last year in sophomore intermediate chemistry. Now, if you recall, when you talked about gases, you developed the ideal gas law, and you talked about something that I'm abbreviating, as you can see up here, as KMT. Do you remember what KMT might refer to if we're talking about gases? Do you remember? Take a guess. Did you say the kinetic molecular theory? Because if you did, you're correct. Now, there were postulates, there were almost axioms, I guess you could call them, to the kinetic molecular theory that we took, that we assumed to be true, and then we were able to develop it into eventually the ideas like the ideal gas equation. So I want to go through those postulates of the KMT, and we're going to talk about whether or not these individual postulates apply to when materials are in the liquid or solid phases. And you're going to hear me use the words condensed phases throughout the course of this unit. So if we say condensed phases, we would be talking about liquids and solids together to distinguish it from the gas phase. So let's remind ourselves about the KMT, right? So there were three fundamental postulates to the kinetic molecular theory. First one is that the volume of the particles is negligible. Now I have here a container that has some gas particles in it. You can see the tiny little red dots. And so we would assume with a gas that the sizes of the particles, as these tiny little red dots in my case, are small compared to certainly the volume of the container in which they reside. And that's clearly true, right? Particles are, we're talking, nanometer scale, we're talking picometer scale sizes. And now the question is that still true if we're talking about these molecules or atoms when they're in the condensed phase? And clearly that is true, right? The size of a molecule, the size of an atom, doesn't change when you go from one phase to the next, right? A water molecule is still tiny. Whether it's in the vapor phase, in the liquid phase, or in the solid phase, the sizes of the actual atoms and molecules, as you know, doesn't change. So that first postulate of the KMT, that the particles have negligible volume, still holds when you're talking about the condensed phases. How about postulate number two, and that is that these particles are in constant random motion. Well, in gases, we know that the gas molecules will take the shape and sort of size of the container in which they reside. I don't do actually a really great job of that because you don't see any particles up here in the neck of the flask, but surely there would be some. So gases do, occupy the volume in which they're in, and they are buzzing around in constant random motion. Now, the amount of constant random motion they have is going to be proportional to the temperature. All the ways they can wiggle and jiggle, and this kind of comes back to entropy, right? All the ways they can wiggle and jiggle will be dictated in a large degree to the temperature. So then, is this still true for liquids and solids? Are liquids and solids, are the molecules or the atoms still in constant random motion? Think about that for a second. In a way, it's a little bit of a trick question, because the answer is, yes, they are. They may not be in as much constant random motion. They may not have as many. Do you remember the term we used when we talked about entropy and all the different ways a molecule could wiggle and jiggle? We talked about the term degrees of freedom. So liquids and solid, or at least molecules in those phases, may not have as many wiggles and jiggles available to them, but the motion is random and it is constant. So where a gas molecule can go wherever it wants inside this container, or a liquid molecule can go wherever it wants sort of in the bottom of the container, and a solid molecule might be stuck in a particular spot within that greater solid structure, but even that solid particle is still vibrating and wiggling and jiggling a little bit. So the idea of constant random motion, that's part of the KMT, still holds. Which brings us to the third postulate of the kinetic molecular theory, and that is that the particles exert no attractive or repulsive forces on each other. Now that's part of the ideal gas equation. We assume that that particle right there is neither being repelled by or attracted to, say, that particle there, or that particle there. This is going to be the fundamental difference between gases and the condensed phases, because this third postulate of the kinetic molecular theory, namely that particles do not exert attractive or repulsive forces on one another, has to be thrown out the window once we get into liquids and solids, because that's exactly what makes a liquid and a solid a liquid and a solid. There are attractive forces between atoms and molecules once we get into the condensed phases. And what exactly are those forces? Well, let's talk about that. I'm going to move my beaker and the KMT out of the way a little bit. We're going to talk about the different types of forces that we have available to us in the condensed phases. There really are a whole set of forces, and these different sets of forces are called intermolecular forces. And I'm going to be like the cool kids, and I'm just going to abbreviate it IMF. Now, different textbooks will treat this differently. Some textbooks use the terms van der Waals forces to refer to intermolecular forces. Other textbooks refer to particular subsets of intermolecular forces as being the van der Waals forces. We won't get lost in that minutia. We're going to use the term intermolecular forces, which is a little bit of a misnomer because it's got the concept of molecular forces in there, but we might be talking about gaseous or liquid atoms or liquid solids, and or atomic solids, and we still are going to be using the term intermolecular forces, but maybe a better term would be interparticle forces. My phone's ringing right now. We're just going to ignore that. So IMFs, they come in different flavors. One intermolecular force is known as the dipole-dipole force. One is referred to as hydrogen bonding, and still another is referred to as the London dispersion force, which I'll abbreviate as LDF, London dispersion force. Now these three different forces, I'm going to explain all of them in more gory detail in the next two videos. The next video will kind of take care of dipole-dipole force, and then the third video is going to take care of the London dispersion force. But one really key idea I need to get across to you. Let's take water as an example. What we're talking about here with intermolecular forces are the attractive forces that exist between molecules. So when we talk IMFs, I can't draw just one molecule. I have to draw at least two molecules, and here I'll draw another water molecule over here. And what we're talking about are the attractive forces between one molecule and another, and I'll represent that by using some dotted lines. These aren't bonds, these are associative forces between molecules. I am not, and I repeat, I am not talking about the forces within a molecule, right? The forces that hold the molecule together, those are bonds, right? Those are intramolecular forces, right? Those are called bonds. What we're talking about in this unit are the dots between molecules. This is maybe not so subtle of a difference, but I guarantee you some of you are going to mix these ideas up as we talk about different characteristics and properties associated with molecules that are a direct result of intermolecular forces. Okay, that's enough for now. Start watching the next video that's going to describe dipole-dipole and hydrogen bonding.